So this is the agenda of my presentation today. So first, I will introduce some backgrounds and motivation of our review, and introduce our methodology in the literature review, and then spend most of the time on the review findings. And depending on how much time we have left, I can also introduce some of our ongoing and future research activities. So the backgrounds, I think many of our audiences here today are working or researching in this energy field. So you might be familiar with those numbers. Buildings account for about 1/3 of the total energy consumption globally, and can consume up to 70% of the electricity and 80% of the peak demand. They also contribute to almost 15% of the direct carbon emissions globally. And if we look at our power system, on the supply side, there's a growing renewable energy shares. So those wind power and solar PV generations, they are more the cleaner power generation, but less predictable and controllable due to the dynamic natures. And on our demand side, since we are decarbonizing and electrifying our power grids, we have increased load variations and more stress on the power grids. So as you can see, the transition of both the supply and demand side imposes some new challenges to the energy management of our power system. And moreover, the climate change is affecting our lives. As a result, we have seen some unprecedented extreme weather events. So for example, in 2020, the Pacific Northwest and California in the United States have seen some record-breaking high temperatures. And similarly, I think earlier in last year, Texas had been through the worst cold snap in the history. So in those situations, when our buildings are trying to run the HVAC system to stay cool during heat waves or stay warm during the snowstorms, the power demand can overwhelm the power supply. And when that happens, there will be some power crisis. So the utility companies have to issue those rotating power outage to avoid some more serious damages to the grid. So so our buildings can play a big role in a reliable and sustainable energy system, can make our grids more sustainable and resilient. So traditionally, I think we have been working in improving the energy efficiency for decades. We're trying to reduce the energy demand. And in addition to that, I think energy and demand flexibility is another important measure. So the term building energy flexibility is really not a new concept. It originates from the demand side management region, which for decades have been applied by the designers and operators. For example, in our buildings, we can shut down some electric appliances or dim our lights when the peak demand is very high. We have high stress on the power grid. And I think in recent years, the grid interactive efficient buildings are becoming an important resource for electric grids in the United States. So basically, it expands beyond the traditional demand side management by integrating some distributed energy resources, such as the thermal and electricity, energy storage, electric vehicles, and also, for example, on-site generations like combined heat and power, and also the solar PV. So those distributed energy resources can enhance our traditional power system. And in addition, we also leverages smart technologies like advanced sensors, data analytics, and controls to actively manage and adjust buildings' load profile to co-optimize for energy costs, grid services, and occupant needs. And there are numerous of initiatives and ongoing programs looking into this area. For example, as I mentioned, in the United States, we have the GAP national roadmap, which is of the research interest of the DOE and also the national laboratories like LBNL. And in Europe, I think there are also a couple of projects. For example, the IKEA looks into flexible management of energy demands at community or neighborhood scales. They also provide some, big data and management and building those data structures, infrastructure to enable more flexible power demands. And there's another project called GoFlex. So this project aims for integrating renewables in the distribution grid. And this program is part of the European Commission's Research and Innovation Framework. And internationally, we also have some collaborations. So those are the IEA, International Energy Agencies, annexes. So for example, we have Annex 67, focused on energy flexible buildings. Annex 81, focused on the data-driven smart buildings. And Annex 82, they are focusing on energy flexible buildings and resilience, resiliences. Yeah, so if we look at more details, researchers are investigating energy flexibility at different scopes. For example, some of them are looking into the system level. This group of researchers, think at all, they developed a model predictive control strategy to control residential heat pump system with hot water storage tank under the real-time pricing scenario. And other researchers look into this problem at the building scale. For example, Ren et al., they developed investigated energy flexibility of a net zero housing using some solar assisted air conditioning system with integrated energy storage. So you can see they have phase change material for thermal energy storage. And they also look into measures to, like for example, for the demand side management via electric load controls. And also at district or community scale, some researchers look into how to coordinate thermal and electricity load demands among different buildings. And I think a researcher group at University of Texas at Austin, they developed this open AIGN, this open source environment that enables different researchers to develop their control algorithms and evaluate their performance to achieve energy efficiency and flexibility. And finally, some researchers look into energy and flexibility at national or sector level. For example, Jerry Langevin at LBNL, they did a large-scale simulation and analytics to investigate, how those energy efficiency and demand flexibility measures would influence the U.S. power system loads in between 2030 and 2050. So we can see there's really a wide spectrum of applications across different scales, and sometimes there's no clear boundary in between. And researchers are trying to answer a variety of questions using measurements, modeling, and control and quantification methods, which I will talk about in the coming slides. So the motivation of our research is, so those questions are still not answered. For example, what is the energy flexibility? How is it defined? There are too many different definitions, and there's no common one. And what are the energy flexibility resources and technologies that we can leverage to achieve flexibility while maintaining other constraints such as occupant and indoor environmental needs? And how is energy flexibility quantified? What are the metrics and key performance indicators that we can use to quantify them? And finally, what are the limitations and future research opportunities in this domain? So those are what we are trying to answer in this review paper. So the scope of the review is only focusing on residential buildings for two reasons, because they account for more than half of the energy consumption in the buildings, and they are extensively studied by the research community. Of course, we can expand this review to include other building types. In fact, in Annex 81 test, we started to review, the data-driven methods and metrics to quantify energy flexibility. So this slide shows the flowchart of how we conduct the literature review. So basically, we start from literature search. We mainly use the Web of Science databases, but we also use like other databases, including Scopus and Google Scholar. So identified 302 papers in the initial step, and further selected 85 papers for more in-depth review. And in terms of the literature review, there are basically 3 components. First, we do some overview of the general information, and then we look into how we can characterize energy flexibility, what are the resources and technologies. And finally, we also look into how we can quantify energy flexibility, what are the metrics, and how what are the calculation methods. So starting from the overview, this is a research trends. So in this bar chart, we can see there's a growing trends in this domain, the growing number of publications along the recent years. Oh, by the way, the review was done in March 2021. So if you do the same search, you will find more papers in maybe 2020 and 2021. So yeah, and the word cloud on the left shows the keywords of those 85 papers that we identified. So you can see demand response, energy flexibility, and some technologies such as thermal storage, and also demand side management are the popular ones. And those 85 papers were published in different journals across different disciplines. So we have applied energies, and some like energy and building journals, and also other IEEE journals and conferences. So this slide shows the geographic distribution of the researchers that are investigating energy flexibility. So we can see majority of them are from Europe, United States, and China. And this slide shows the applications in the review studies. So basically, we can describe application of energy flexibility in this structure. Basically, we cover scope, which are system level, building level, district level, and sector level, and the phase, which includes the phase of the study in the building life cycle, and the purpose, which includes, for example, the potential evaluation and control strategy comparison, and also, for example, during the building design, we can compare different parameters and evaluate how they would influence the energy flexibility. And finally, we have the methods. So based on whether there are optimization involved, they can be heuristic or rule-based, and of course, we can have optimum methods involved here. So to illustrate what I mean, I can share 2 examples here. So you can see in the first example, to evaluate different envelope parameter influence on the building's capacity to shift cooling and heating demand, which is the purpose. In the building design phase, the peak power reduction, which is a matrix, can be used, and the evaluation is done with parametric simulation. So there's no optimization involved here. And similarly, we can describe this kind of application following this structure. So this tree map basically shows the number of studies at different scales for different purposes. So we can see the majority of them focusing on system level, building level, and district level, and only a few of them focused on the building sector or national level. And in terms of the performance, there's really a wide range of them. So with peak power reduction of 0.5% to 65%, and energy savings up to 60%, and operational cost reduction of 0.8 to 48%, and greenhouse gas emission reductions of 0.4 to 29%. So you might ask, why do we have those different perspectives and wide range of savings? That's because, as mentioned earlier, the researchers are looking to different systems. They have different objectives, and usually it's hard to compare their performance with a single metric. So next, talk about the characterization. So in this review, we classify the flexibility modes into 4 types. So first type is load shedding. So basically allows the buildings to cut the demand during the peak hours. And this kind of load shedding usually needs to reduce the demand within a few minutes upon receiving some signal from the grid, and usually has to last for a couple of hours. The second mode is called load shifting. So basically, we want to take advantage of cheaper or cleaner energy by shifting the demand from one time period to another. So we can see shedding and shifting are the 2 most popular flexibility modes in the articles that we reviewed. And third mode is called modulating. So basically, we want to control the building to maintain a certain frequency for the power system voltage. So this usually requires the buildings to respond in very short periods, and also and finally we have this generation, which basically uses on-site generation such as rooftop solar to reduce the losses on the grid and reduce the needs for more power plants. Yeah, so that's the load profiles and flexibility modes. And next is the resource and technologies. So basically, what do we need to enable the energy and demand flexibility in buildings? So we can classify those resource and technologies into 4 types. The first one is thermostatically controlled loads, or TCL for short, with active or passive thermal energy storage. And the second category is electricity storage, such as batteries, electric vehicles. And third type is electric appliances scheduling. And fourth type is the energy hub. So this is usually used for a neighborhood or community, which involved energy conversion, storage, and fuel switches to provide flexibility. And those technologies can basically be divided into end users and associated facilities. So end users are the equipment or system that can change their energy use behavior to allow those load shedding, load shifting, and modulating. And associated facilities are the infrastructures that can support those kind of energy use change by the end users. So for example, end user can be our HVAC system. So we can pre-cool and preheat our building by adjusting the thermostats. This kind of behavior needs to be supported by some sort of energy storage, such as the passive thermal mass. Yeah, and in addition to the resource and technologies, we should also look into the building services, because we do not want to damage our building services because of the flexible operation. So in our review, we found that only 55% of review articles actually explicitly consider those impacts. And as you can see, among those studies that consider those services impacts, most of them only consider like 1 aspect, and some of them consider 2 or 3 aspects. And those aspects includes thermal comfort, followed by hot water surfaces, appliances, mobility, and lighting quality. So the reason that we see a lot of study consider thermal comfort is there's widely acceptable metrics to evaluate thermal comfort, while there's clear gap in like metrics to describe other services. And then let's take a look at the quantification. So here we are interested in the modeling, analytics, and software tools. So for model types, basically there are physics-based models. Those are the detailed model with very full detail of building characteristics. And there are also hybrid models, which are usually the reduced order models with parameter identifications. And we also have the data-driven models, which are like pure black box models. So we also have the level of details, which indicates, how much detail, how much information we need about the system in order to model it. So we can see that for data-driven models, usually we do not need too much information because it's pure data-driven, pure black box. And for hybrid and physics-based models, we would need more details about the system type and configurations. In terms of software, so basically there are 4 types. The first one is the whole building energy modeling tool, such as energy paths, trances, and IDA-ICE. And some other tools, including Python or Java or other programming languages. So the users can use them to write their own equations to describe the system and to do the modeling. And we also found researchers using statistical softwares and also optimization software such as MATLAB and games and so on. So there's really plenty of software being used in this domain. And in terms of the data needs, here we take a look at the approaches to get the data, and also temporal resolution, and what kind of optimization were involved. So we can see the majority of the studies are based on simulations, and only a few of them have the real measurements involved in this process. In terms of the resolution, about 2/3 of them used hourly resolution because those are sufficient for load shedding and shifting. But for other flexibility modes, such as the modulating, we usually need resolution with higher granularity. Usually we need sub-hourly. And for optimization, about 43% of studies has some sort of optimization in their quantifications. And here is a distribution of their methods. So lastly, I also want to mention applications of the building controls to provide energy flexibility, which is a topic of growing interest. We found 43 out of the 85 studies investigated control and energy management strategies to realize the energy flexibility. And basically, they mainly use 2 types of models: the detailed physics-based models, developing energy paths, trances, and IDA-ICE. They usually have very high resolution or high accuracy if you model it correctly. But those models are, it's not differentiable, so it's hard to implement optimization algorithms to realize the full potential of the energy flexibility. Other types of models are reduced order models, developing MATLAB and Modelica and other softwares. So those are feasible for gradient-based optimization approaches. And there's also a growing trend of studies in pure data-driven based building controls, such as the reinforcement learning controls, but the number is still limited. So you can see this the number of publications in the recent years color-coded by the control methods. And next, let's take a look at the metrics to quantify the energy flexibility. So here are the key messages. First of all, there is a lack of commonly agreed energy flexibility metrics. Only 58% of them have a clear mathematical definition of the energy flexibility, which means we can calculate with the equation. And among those 58% of study, which are 49 papers, we found 61 unique energy flexibility metrics, which covers 6 different performance aspects, including energy, power, cost, the duration of the load change, carbon emissions, and comfort. So you can see really researchers tend to define their own metrics, and there's no commonly agreed metric for this problem. And another finding is that usually those quantification metrics require both flexible and the baseline scenarios. But sometimes there are challenges, which I'll talk about in the next slides. So this table shows the top 5 most popular KPIs that we reviewed. So I won't go through the details of those metrics, but the key message is that those metrics themselves require different level of inputs. So for instance, this the peak demand reduction is very simple index. It only requires the peak demands of the flexible and baseline scenarios, while other metrics, for example, the self-sufficiency and self-consumption, they require the PV generation and the building load profiles for the whole day. And also they have different performance aspects. Some of them are designed to indicate how the power is changed during the flexible operation, while others can reflect energy, cost, emissions, and other performance aspects. So basically, this is the workflow of how we can calculate the KPI. So I will use simulation and measurements as an example. So for simulation, the first step is we need to do the modeling. We need to build the model, calibrate it, and we can use it for the simulation. So usually this process is very hard because it takes effort, takes expertise, and it's very time consuming to build a model and calibrate it. But once we have the model, we can run simulations and easily get the baseline and flexible load profiles. And then from there, we can calculate the KPIs that requires the baseline, the KPIs without baseline. So you can see the key challenge here is the modeling part. On the other hand, for the measurement path, we need to first do the sensing and metering. It's relatively easy if we have the metering infrastructure. And as for the load profile, it's easy to measure one scenario, but it's hard to identify the baseline, because if you imagine our building operation is very dynamic, the weather will change, the occupant will change, the internal heat gain will change. So it's really hard to measure this baseline load profile in a standardized way. And the rest of the calculations are similar as the simulation-based approach. So yeah, another challenge is that we can see most of the KPIs requires the baseline, whereas only a few of them can indicate the energy flexibility without the baseline scenario. And I also would like to share one example of how we can calculate the EF KPI with the existing data. So here we use a metric called flexibility factor, and it's defined by this formula. In this case, it does not need a baseline, and we do need the demand response start and end time. And in this example, we use the HVAC system equipment runtime, which is the fan runtime, to as the input of the formula. So you can see this time series chart shows the fan runtime and also the cooling set point, the indoor air temperature trends in a typical summer day. And this data is from Ecobee smart thermostats. And also have two areas. So the green shaded areas indicate the power price is low, and the red area shows where we have high price for electricity. And the formula works like this. So imagine if all of our fans runs during the demand response time period, which is the high price periods. This value will be -1, which is really poor, right? Because we want our system to run outside of this high price periods. Whereas, if we run our fan all inside this long DR period, which is low price periods, this value will be 1, which is ideal. So you can see we can use this kind of metrics to guide our building operation. For example, I know I should probably pre-cool my building before the high price, and this kind of metrics can tell me how well I'm performing. Yeah, so previous slide shows the characterization and quantification, and this slide shows the research gaps that we summarized from this review. So the first one is, what is energy flexibility is still an open question, and definitions sometimes are ambiguous. And formulating a one-for-all definition is very challenging due to the diverse nature, because we can see a wide range of applications at different scales. And the second question is how to represent energy flexibility resources in a standardized way. We see that researchers tend to build their own models, they have their own metrics, and sometimes their models are not interoperable. It's not easy to use those models at scale. And third question is how to quantify energy flexibility potential of a whole building, right? So sometimes, for most of the times, researchers only look at one aspect of the building, only focus on certain systems. But how can we, combine and integrate those different systems and unlock the flexibility potential of the whole building is still an open question. And finally, how to define the requirements and provide credits for energy flexibility of buildings in the energy codes and standards, and also the rating system or policies. There's still a lot of room for us to do. So as far as we know that the US GBC need green building standard, they started to include this pilot credit to incentivize the flexibility of buildings based on some metrics, based on this New Building Institute Great Optima initiatives. But yeah, I think there's still a lot of room for us to do in this area. So yeah, since we have some more time, I can share some ongoing future research opportunities. So the first one is standardized energy flexibility characterization and quantification. And this slide shows basically the existing data tools and schema ecosystems. So at the bottom layer, we can see we have the terminologies and dictionaries, such as the unique building identifiers. This is a building energy data exchange and specifications. And if you're energy modelers, you might be familiar with EnergyPath. So it has a dictionary to define, different building components and systems and equipments. In the middle layer, we have data schemas such as the HP XML and Building Sync. Those are used for the data exchange. And we also have some metadata and sensor schemas. For example, the Project Haystack and Brig are very popular recently. And for building information modeling, we also have IFC and GBXML, those schemas are also widely used. And built upon the schemas and dictionaries, we have a group of applications. So for example, in the United States, we have Portfolio Manager and an audit templates for data connection. Also have application for data management, for example, the Seed platform. And also have the modeling, analytics, and evaluation applications. However, as you can see, although we have those existing schemas, the energy flexibility is still an open area. So one future opportunity is we can develop an energy flexibility ontology to answer those questions. So what are the energy flexibility resources and how to describe them in a commonly agreed way? And how do we model flexible operations? How do we define the inputs and outputs? And how do we quantify the flexibility using the metrics that I just showed? And this is an ongoing work. So we're developing the EF ontology. So basically, it has those 6 components. The first of all is the application scope. As I mentioned earlier, we cover system building, community levels, and performance goals includes energy, cost, peak demand, and carbon emissions. And building services would include, how the flexibility operation would impact on which kind of building services, for example, the IEQ, the thermal comfort, air quality, and so on. And then what are the flexibility resources? What are the technologies and associated infrastructure that enable the flexible operations? And also the flexible load characterization, how to describe those load profiles. So for example, how long does it take to change our loads, and how much load we can reduce, and how long can we keep the reduced load? Those are the temporal characteristics that we are interested in. And then finally, the EF KPI module will describe which KPIs are available, what kind of performance aspect do they indicate, what kind of data they require, and how to calculate them, who are the stakeholders are interested in them. Yeah, so another research opportunity is to do this data-driven energy flexibility quantification. So as I mentioned earlier, for the simulation path, the modeling is really very tricky, very time-consuming. So the research question is, how can we develop simple but accurate data-driven models that we can use later to run simulations under different scenarios to generate those load profiles? And the second question is, how can we standardize the measurements process so that we can get both the baseline and the flexible scenarios? So as you might be familiar with, HVAC system industry, actually have very standardized and commonly agreed way to test and read the system performance. So basically, they test the HVAC equipment under different conditions and integrate those into a single indicator. So how can we do this? Can we do this for building energy flexibility? Is still an open question. And finally, can we develop some good KPIs that do not need the baseline load profiles? If we can do this, we do not need to worry about the measurements for different conditions and also the modeling of the building energy systems. And another research area is advanced building controls to enable energy flexibility. So there are a lot of ongoing researches. So our research group developed this alpha building residential community, which is a multi-agent open AI gym environment for thermally controlled load coordinations. So this picture shows basically the structure of the environment. We connected, individualized thermal preferences of the people, and those can be used as the temperature set point schedules. And then we also identified some reduced order thermodynamics models from the connected smart thermostat data. So those models can be used to simulate how the temperature will change under different set point schedules. And we also include other data sources such as the weather data and also the internal heat gain schedules. And we integrate those information into this environment that the users can develop their control agents or different control algorithms and test their algorithms using this environment. And on the right-hand side, we show an example of TCO controls for load tracking. So basically, you can see the green line shows our tracking targets, and we want a community of residential buildings to control their buildings TCL to follow this trend. You can see basically we try different control algorithms, and we can use this to evaluate how it performs in this environment. And another research activity is called CityLearn. It's also an open source OpenAI gym environment. This is developed by a group of researchers at University of Austin. So their environment can be used for implement multi-agent reinforcement learning for building building energy coordination and demand response in cities. So I think, yeah, there's still some development involved, and the researchers are still trying to improve their environments and testing different control algorithms. So it's really exciting research area. Yeah, I think that's the last slide of my presentation. And yeah, thank you for your time and listening. Happy to answer any questions.
Okay, thank you. Thank you for your interesting report. And the demand side management is really critical because many previous low carbon research focus on the supply side, but I believe that in addition to generating clean energy, clean electricity, the smart use of electricity is also important, and it's a key to support flexible electric grid operation and promote carbon neutrality. And
Right.
besides, the OpenAI gym environment is very important. It's a kind of infrastructure for the energy research. So thank you. And so is there any questions? Let me see. Okay. Okay. Is there any question on Bilibili? Okay, so there are two questions. What is the sampling standard of the questionnaire? And what books do you recommend? That's a question from the listener.
Sorry, could you repeat that? So questionnaire for...
What is the sampling standard of the questionnaire? And what books do you recommend?
Sampling standard for the questionnaire. Actually, we did not use any questionnaire. Did you mean how we search articles during the literature?
Yeah, I think it's about the 302 literatures you have mentioned.
I see,
maybe
I see.
I'm not quite
yeah,
sure.
So
because
as I mentioned, we use the Web of Science database. I think it's which is commonly used in the research community. So basically, you can specify which topics you're interested in. For example, in our case, we're interested in residential energy flexibility. We would type in some keywords like residential buildings, communities, and maybe energy and demand flexibility. So this that will give you a list of articles that are relevant and recent, and then we export those articles and did some manual screening. That's why we get those 85 papers out of the 302 papers, and then we do more in-depth review for those papers. Basically, that's how we select the articles.
Okay, I see. And the second question is, what books do you recommend? The listener is very curious about the books, maybe about this topic.
So to be honest, I'm not aware of recent books on this area, but there are a lot of interesting papers and reports. Like I mentioned, if you search for the GAP, which is the national roadmap for great interactive efficient buildings, it actually have some very insightful and useful information in this report. And also, if you go to the website of those annexes, I think they have a list of publications that are relevant to the research activities. I think, yeah, those are good sources.
Okay, I see. Okay, so is there any other question? Anyone can apply to unmute because everyone is muted now. So you can just apply to, let me see, there's another one. Okay, so is there any flex rank for the adjustable resources or something like that? I'm not quite sure about this question.
Some
it's
range?
called flex rank. Flex rank.
Flex, okay. Flex rank. So you're referring to some sort of metrics or? Flex rank.
Yeah.
Yeah. So, yeah, like we showed in this slides, you can see there's really a lot of different definitions of flexibility. We have different metrics, and sometimes they have very similar formulas or equations to calculate those metrics. And I think it's hard to rank the flexibility, right? Because you have to consider different perspective, energy, power demands, and cost. So sometimes we have to use multiple metrics to compare, but not a single rank.
Okay, thank you. And there's another question. Is that possible to share these slides?
Yes, of course. Yeah, I can share the slide with maybe with you, and you can distribute it. Or I don't know what's the best way to. Yeah, or you can reach out to me at the email address at the end of the slide here.
Okay. Yeah. And probably you can just upload it to the GitHub if you want. I see you have a GitHub link.
Yeah, but that's for another project. Maybe it's better to to share.
Oh,
with
okay,
you and,
I see. Okay, I will deliver that to the others. Yeah, thank you.
Problem.
So it seems that there's no more questions, and
great.
Yeah. Okay, so that's all for today's seminar, and thank you all for participation, and thank Mr. Lee for your wonderful report. And please continue to pay attention to energy visions. And thank you, everyone. Have a good day.
Thank you for your time and attention. Yeah. Bye.
Yeah. Bye-bye.